Got it.
You threw it at me first, Mr. Burkham.
You know why I don't teach freshmen?
Because they're a bunch of idiots.
Exactly.
Like these two.
I would need a reason to throw
Merry
it.
Christmas.
Okay, so here's what we have left, is just these multiple choice questions. And this is also going to be a lot of what your assignment is going to be on today. So you have two primary equations that you're going to deal with. One is the oscillating mass, 2 pi times m over k. If you have a pendulum, it's 2 pi L over g. So, and it's hard to emphasize this enough, that you have to look at what is a factor and what is not a factor, okay? One of the most important things. So, if you talk about the mass of what's on the end of the spring, hey, mass is a factor when it comes to an oscillating spring. On a pendulum, it doesn't matter. Gravity is a factor when it comes to pendulums, but it's not a factor when it comes to an oscillating spring. Okay? Mainly because of the fact that the spring has the capacity to store its own energy and oscillate back and forth. If you don't have gravity and you lift up a pendulum and let go of it, it's just going to stay there because it doesn't have any capacity to convert that stored potential energy into kinetic energy, but a spring does, okay? So that's one of the reasons. The other thing you need to look at is what's underneath the radical. So if you look on like question number 1, Bob is attached to the end of a light rod to make a simple pendulum. So right away, you know you're going to be dealing with 2 pi times the square root of L over G. You know that, okay? That's your go-to equation. Now, this one is relating to frequency. So what I would recommend is that, and this is going to be important today, is that period and frequency are inverses of each other, okay? So wherever you see T, you can put, oh, that's 1 over frequency. Same idea. So if that's the case, then we're going to take 1 over that whole thing. So to get the frequency of the pendulum, that's 1 over 2 pi times the square root of G over L. So now that's how you're going to look at the period or the frequency of a pendulum, okay? Because they're inverses of each other, okay? You also should be able to look at the units and go, okay, well, this is a pretty easy dimensional analysis. That's meters per second squared divided by meters. The meters cancel out. You get 1 over second squared, and the square root of that. That gets you 1 over seconds. That's what frequency is measured in, okay? So that's a simple way. It's like, God, did I do this right? Look at the units. If you get 1 over seconds, you did it right. You got frequency, okay? It's cool. All right. Now, so if you look at this one, it says, now if the bob of mass of 4m is attached to the right rod, the frequency of the oscillation for this new thing is blank. So did they even have to tell you on there that a mass of 4m is attached? No, it isn't part of the problem, okay? They told you that, it doesn't matter, because there's no way to put mass into the equation of a pendulum. Now, does it matter the fact that the length was 4L?
Yeah.
Yeah, that matters, because that's part of the equation, okay? So then, once you figure that out, you can go, okay, well, that new frequency is going to be 1 over 2 pi times the square root of G over 4L. Well, what's the square root of 4? 2. Okay, there you go. All right. Now, when you get to like question number 2, simple harmonic oscillator, 4 kilogram mass into the spring. Speed of the mass as it passes equilibrium is 10 centimeters per second. What is the amplitude of the mass's oscillation? So this is going to be important in a situation like this. So when you have an oscillating mass, okay, on a spring, you have 2 extremes that you can look at. You can look at where it's all us, and that's gonna be 1/2 Ka squared, okay? Which is just a fancy way of saying 1/2 Kx squared, but I'm gonna use amplitude because that's when it's at its greatest point in the oscillation, okay? So 1/2 Ka squared, don't look at that and go, oh, that's fancy. We have capital A, right? It's just 1/2 Kx squared. We just set it equal to the amplitude, okay? Now, when is it gonna have its maximum velocity? Yeah, the center. If you're at the center, what's the value of your amplitude? So that has to equal your kinetic energy, which is 1/2 m B max squared. So if you ever know what the amplitude is, you can figure out what your maximum velocity is by setting those two values equal to each other. Okay? When you get to that last question on 8, what you want to look at on that one is that they've got a position time graph and a velocity time graph. Keep in mind that both graphs have to show the same thing happening at the same time, okay? So if you have a position time graph, say something like this, and this is your position time graph, and you draw a horizontal line at that relative maximum to get an instantaneous velocity of 0, your velocity has to go to 0 at that point. So that's a simple way to try and the process of elimination is to go, okay, which ones have velocities that are equal to 0 when the position time graph has tangent lines equal to 0? When you have your maximum velocity, oh, that's in the middle. Which graph picks on that? So just a word of advice. Keep in mind on question number 4 that there are 2 springs, okay? I'm just saying, keep in mind the fact that there are 2 springs, all right? Any questions on the multiple choice? Yes, you should have some answers that are C. Connor, yes.
Since there are 2 springs there, does that mean you
Huh?
can't, since there are 2 springs on question 4, that means you can't use the spring potential equation, right? Does it? I don't know. I tried it that way, and I got it wrong. So I was looking 5 minutes ahead.
Look at it in terms of, it has nothing to do with energy. It has to do with the force elongation graph.
Okay.
Start with that.
I mean, I got it. I got the right answer doing it.
Okay. All right. Any other questions on the multiple choice? So here's how I went this sequence. Okay? So basically in the order in which we did it. So the white paper first, then the blue paper, then the purple paper, and then the graph on the back.
So do we have two? Oh, hey, this is weird. All the papers are hand in hand are the same size.
You gotta use a screwdriver.